Good morning, all of you. So today we'll discuss dispersion by a prism. Okay. In the last class, we have discussed refraction through a prism. In this class, we will discuss dispersion by a prism. Okay. So when a ray of white light passes through a prism, it not only deviated but also splits up into its constituent colors, and you will see the colors in the following sequence: Vibgea, violet, indigo, blue, green, yellow, orange, red. Okay, so this display of colors, this splitting of white light into its constituent colors is known as dispersion, and the display of colors is known as spectrum. Okay, so and the spectrum of light was first observed by Sir Isaac Newton in the 17th century. When you observe the spectrum of light, naturally one question arises: so how do you get different colors from the prism? Whether the prism somehow creating the colors, or does it only separate the colors already present in the white light? Okay, and this problem was solved by Sir Isaac Newton. He placed one inverted prism adjacent to the actual prism. This is one prism. Okay, it is producing, it is separating the white light into its constituent colors. So he found answer to this question. He placed another similar prism but in an inverted position. Okay, so he found that he placed this prism such that the emergent beam from the first prism incident on the second prism. So he found that the emergent beam again the white light. So he concluded that the prism is just separating the colors already present in it, and the second prism just recombining the colors into white beam. Okay, so and we know that each color has its own wavelength. Okay, different colors has different wavelengths. Okay, and the wavelength, red color has longest wavelength, and violet has smallest wavelength. Okay, so the question is why this dispersion phenomena takes place. The question is why dispersion takes place. Why dispersion of light takes place when it passes through the prism? Because the refractive index of the medium is a function of the wavelength. Okay, the refractive index depends on the wavelength of light. Okay, refractive index of the medium, so it depends on the wavelength. As the wavelength changes, lambda changes and also changes. So we can say that the medium offer different refractive indices for different colors of wavelengths. Okay, so here you can see the figure. This is a violet. So violet bends most, and this red bends least. Okay, so here this prism is offering more refractive index for violet and low refractive index for red. Okay, and then you compare the speeds. What do you get? Speed V is equals to speed of red color. You can see so what is the expression of speed? Speed equals to frequency into wavelength. V equals to nu lambda, red color wavelength. So and the violet, let it be VV, equals to nu into lambda V. So since the frequency is constant, it depends on the source, not and the medium. So frequency is constant. Since the since since lambda r is greater than lambda v, wavelength of red color is more than the wavelength of violet light. The so speed of red is more than the speed of violet. Okay, red color travels faster than the violet light. Whenever light one of the light travels faster and the other light travels slower, definitely, and one of the light is bending in one uh, suffers one type of bending, another suffers another type of bending. Definitely the colors, you will find some separation in the colors. That is the reason why they are splitting into different colors. That is meant by dispersion. So dispersion takes place because of the refractive index, change in the refractive index of the medium. Okay, this is the reason for dispersion. And here this glass medium is acting like a dispersive medium. But when same white light passes through air and any vacuum, it doesn't splits into constituent colors. Why? Because it is not offering different refractive index for different medium, different colors. Okay, so that air are nothing but air or vacuum are said to be non-dispersive medium, where glass is a dispersion medium where light rays are splitting into different colors. This is about the dispersion. Okay, and the next you can see the violet, different colors, uh, and the wavelengths and refractive indices values for different media. Okay, when violet light of wavelength 396.9 when travels through a medium of crown glass, it is one type of glass. So that crown glass offers 1.533 refractive index, and the flint glass offers a refractive index for the same light, so as 1.663. Different medium offering different wavelength to the same color. Okay, so and the blue light of wavelength, this is a blue light wavelength, and crown glass offers this refractive index, and flint glass 1.639. Okay, this is about the dispersion of light. Now we will discuss some natural phenomena due to sunlight. So and and we'll see the different colors in our daily life, like mm, a rainbow, and the blue color of the sky, and wings, colors of wings of birds, peacock, and many examples. So we'll see some of the examples we'll discuss in this class. First one is rainbow. Okay, we'll discuss the formation of rainbow. Actually, the rainbow is an example of, it is an example of dispersion of light, by water droplets in the atmosphere. Okay, so actually this phenomena, rainbow, is the formation of rainbow is a combined effect. Actually it is a combined effect of dispersion, dispersion refraction, and reflection. It is a combined effect of dispersion, refraction, and reflection. Okay, and what are the conditions to observe rainbow? So when we see this rainbow in the sky, and then we'll discuss the formation of rainbow. So what are the conditions to get a rainbow? Conditions that are the conditions are, so in order to see the rainbow in the sky, let it be the earth and this is the sky. So in order to observe the rainbow, sun should be shining in one part of the sky, and there is a raining in the other part of the sky. For example, sun is shining the western hemisphere, and there is a rain in the eastern hemisphere, and observer on the earth can see the rainbow when his back of the person should be towards the sun, and then only he can see the formation of rainbow. Now how the rainbow uh, formed we will discuss here. Right, you'll see this figure. So this is the mm, let us take, in order to understand the formation of rainbow, let us take a spherical water droplet, rain droplet. I'm taking a single rain droplet which is in a spherical shape. Okay, so when sunlight enters the rain droplet, so here it splits up into, it's it separated. So first refraction takes place, and these colors are separated because the different light rays are bending differently, and different light rays traveling uh, with different speeds. That is why separation of these colors takes place. We are representing only two colors here, red and violet. We are not representing the intermediate colors. So figure become complicated. So will be complicated. That is why we are representing only red and violet colors. So when light falls on this first surface, the refraction, due to refraction, so they splits up into different colors. And when the incident on the inner surface, say if the angle of incidence, when here the angle of incidence is more than the critical angle, so and this is water air surface, since the light ray is traveling from denser, this is a denser to rarer medium. When the angle of incidence is more than the critical angle, actually a ray of light incident at an angle more than the critical angle for air water surface is 48 degrees, then it suffers total internal reflection. So it gets at the inner surface, this these light rays internally gets reflected and emerges out from the spherical water droplet after one more refraction. Okay, so here the separation further increases. Here uh, here they are separated, so and they are at the second inner surface they are internally reflected, and at the second refraction the separation between the colors further increases so that we can see the rainbow. Okay, here 40 degrees and 42 degrees are the angle between the violet angles, angle of emergence for the violet uh, mm, and red with respect to incident light. Okay, if if you are eye in this position, then only you can see this seven colors. If you observer is in this position, he cannot see the rainbow. Okay, so next you will see the next one. This B and C figures represent the primary and secondary rainbow. This is about the primary, and the next one is secondary rainbow. So primary rainbow is a three step process. It is a three-step process. Okay. So what happens here? This is an observer. Here, observer is located. When sunlight passes through these two rain droplets. I am taking two rain droplets. So this is sunlight. Okay. So here. Only here the splitting is not represented here, final splitting represented here. So after refraction, so after second refraction, so we'll get dispersion of light. Okay, so for example, observers can see red colors from the top droplet, and if he is in a position to view a red color from the top droplet and violet color from the bottom droplet. So okay, so and this is when he is in the position to see these colors, this is called primary rainbow. Okay, so mm, and and he cannot see the violet from the first droplet and red from the second droplet. Okay, so right. Next, this a uh, secondary rainbow. Okay, so secondary rainbow, in the second rainbow is a four-step process. It is a four-step process. Okay, so in this phenomena, uh, so observe it here. Two refractions and two reflections takes place. Okay, in the second rainbow the order of colors are reversed. In the primary rainbow, so what are the colors you'll see in the primary rainbow? Observer can see red on the top and violet on the bottom. In the secondary rainbow, the observer can see violet on the top and red on the bottom. Okay, and see this observer uh, can see the rainbow, secondary rainbow, but with lesser intensity. The intensity of the light decreases. Why? Because it suffered two internal reflections, so the intensity of the secondary rainbow decreases. And so this is about the formation of the rainbow. And the next topic is scattering of light. Okay, so when light passes through the atmosphere, it gets scattered by the atmospheric particles. Light gets scattered by scattered by the by the atmos atmospheric particles. Atmospheric particles. Okay, and here light, shorter wavelength light, it is observed that shorter wavelength light suffers uh, much more scattering, than the longer wavelength. Then the scattering for a shorter wavelength is much more than the longer wavelength, and the amount of scattering is inversely proportional to fourth power of the wavelength of the light, and this is the relation is given by Rayleigh. So, and the scattering is known as Rayleigh scattering. So this is just observation. So what happens when light passes through atmospheres, and light gets reflected, scattered by the atmospheric particles, and it is observed that shorter wavelengths are scattering much more than the longer wavelengths, and the amount of scattering is inversely proportional to the fourth power of the wavelength of light, and this is observed by Rayleigh, so it is known as Rayleigh scattering. Okay, so the question is why the color of the sky, why uh, sky appears blue, in color. Okay, so here blue, the wavelength of blue is smaller than the red color. So as I told that charter wavelength suffers more scattering. So blue color suffers more scattering, suffers more scattering. So than the red color. So it will be scattered in different direction. But compared to violet, so compared to blue, actually violets uh, scattered much more than the blue light, but blue is more sensitive to eye, then that is why we'll see blue color of sky. Okay, so here the scattering not only depends on the wavelength of light, so but also depends on the size of the size of the scatterer scatterer. Okay, for example, scatter nothing but atmospheric particles. Okay, let A be the size of the scatterer. If A is very much less than the wavelength of light, then Rayleigh scattering takes place. Rayleigh scattering takes place. So what it means, when size of the particle is very small compared to the wavelength of light, Rayleigh scattering nothing but shorter wavelength suffers more scattering, and you can see from this expression amount of scattering is inversely proportional to fourth power of when lambda is large, when lambda is large, scattering is small. When lambda is small, scattering is more. So shorter wavelength suffers more scattering. Okay, so that is applicable when the size of the scatter is small, much very much smaller than the lambda. But when the size of the scatter is very much greater than the wavelength of light, then light behaves differently. For large scatterers like dust particles in the atmosphere and water droplets, light passes through water droplets and dust and ice. So it behave differently. Okay, so Rayleigh scattering does not take place. Okay, so almost all the colors scattered equally. When the size of the scatter is more, so all colors, almost all colors scatters scatters equally, nearly equally, not exactly, nearly equally. So we cannot see domination of one color in the sky. Example is the cloud. Clouds appear white. Clouds appear white because so clouds contain water droplets. Water droplets. Their size is very much bigger than the wavelength of light. Then hmm, then we can see scattering of all colors equally. When all colors are coming equally, okay, then we'll see white light. We cannot see the separation of the colors. All the colors are reaching uh, mm, so in the same direction, so we can see the white color of clouds. Okay, and one more example is the sun appears red during sunset and sunrise. I'll remove first it. No, this is the position of the sun appears red during sunset and sunrise. When the during sunset and sunrise, sun is near the horizon, so the distance between the sun and the position of the observer is very long. Okay, so okay, so and during noon session, the distance sun is nearly overhead the observer and the distance is small. Okay, so and here the distance is large. During the journey of white light, all the colors, all the longer wavelengths are scattered, all the shorter wavelengths, all the shorter wavelengths scattered by scattered and least scattering light, that is red color scatter least. That light reaches the observer. That is why we can see the red color of the sky, red color of the sun during sunset and sunrise. Okay, we can give another explanation to the scattering of light. Actually, what is the scattering? When we'll discuss in atomic and molecular level, let us take an atom or molecule H2O. Let us take H2O molecule in the atmosphere. Atmosphere contains nitrogen, oxygen. Major amount of gases are nitrogen and oxygen. Okay, and water vapor, also carbon dioxide, etc. Okay, these are the major amount of gases. So 78% of atmosphere is a composition of nitrogen and oxygen. Okay, so when light incident on the atom or molecule, light incident on the atom or molecule, some amount of light is absorbed and re-emitted in different direction. So this light incident on the atom, this is an atom, so it is re-emitted in different direction. This is a basic process that will happen in the process of scattering. Okay, so so light, this atom does not respond to all the light. When the size of atom comparable with the wavelength of light, then only it responds and it absorbs the incident light and vibrates. This atom vibrates. During this vibration, it emits light in different direction with different intensities, and it is observed that the intensity of intensity of scattered light intensity of scattered light is maximum uh, at 90 degrees. 90 degrees. Okay, so when you observe the sun when you observe the when the scattering is perpendicular to uh, sunlight, if you see the scattering perpendicular to sunlight light rays, you will see the maximum intensity of scattering. So if the angle of view changes, the color of the sky also changes. So it looks a dull blue like that. Okay, the angle of scattering is maximum at 90 degrees. If the angle of scattering is, for example, this is an atom, so this is incident light. If the angle of scattering is 90 degrees, this is the angle of scattering. If the angle of scattering is 90 degrees, you will see the perfect blue appearance, a clear blue appearance. If you see in this position, if the rays are coming like this, if you see the sky in this position, you are able to see the blue light, but it is a dull blue. Okay, the why? Because it is intense, its intensity is different for different angles of scattering. Okay, and right. So, but the question is, why a blue color scattered? Why? Because here the size of nitrogen and oxygen is comparable to the wavelength of blue light. Okay, wavelength of blue is comparable to the size of the nitrogen and oxygen. So major amount of gas are oxygen and nitrogen. Nearly their size is nearly equal when compared to the wavelength of light. So they absorb only blue light. Okay, since the wavelength is nearly equal to their size, so blue light is absorbed by these atoms. Okay, and they are re-emitted in different directions with different intensities. That is why we see blue color of the sky. Okay, this blue color of the sky. And when there is no atmosphere, for example, when there is no atmosphere, what would be the color of the sky? When there is no atmosphere, so the sky appears black. Okay, so we have answered some questions here. Now the color of the sky is blue because of the scattering of light. Why only blue? Because their size. In the molecular concept, we can say that the size is comparable with the wavelength, but blue is more sensitive to the uh, that is why we see blue color. Okay, this is about some natural phenomena. So, of due to sunlight, we have discussed rainbow, formation of rainbow and scattering of light. Okay, so that's